Well, hello everybody, and good afternoon. So my name is Tony Shin. I'm a PhD candidate here at the University of Michigan, researching with Professor Pozzi. I'd first like to thank everybody for being here, and thank you for allowing me to talk to you all on some of the preliminary research results I have from our recent measurement campaign at Idaho National Laboratory. So today I'll be talking about the development of an active mode counter for a fast neutron multiplicity counter. So just some basic introduction and background. There's always a need to advance our technology to better our ability to verify and monitor these special nuclear materials. One of the techniques that we use, that is used generally, is neutron multiplicity counting. So an item that fissions will emit multiplets of neutrons ranging from anywhere from 0 to upwards of 10 or greater. This technique is a non-destructive assay technique. And there are two modes of operation. There's a passive mode and an active mode. Passive mode, as many of you know, is just passively counting, whereas active mode, we're driving these induced fissions in our uranium samples. So traditional NMC systems, they utilize capture-based thermal neutron detectors. These NMC systems are typically in a well-type geometry. So there's a schematic shown on the bottom right image there, where the blue would indicate the cavity where the sample would be placed. Again, this relies heavily on primarily helium-3 based detectors. That's, as everyone knows, is the gold standard for thermal neutron detectors. Due to the increasing cost of the helium-3 detectors, there's been a lot of research efforts to investigate helium-3 alternatives. So University of Michigan and INL have been collaborating on the fast neutron multiplicity counters, and our primary detector that we focus on are organic scintillators. So our system is comprised of two different types of organic scintillators, shown on the top left image there. So we have an EJ309, which is a liquid organic scintillator. It's 3 by 3 inches, and we also have still beam crystals, which are 2 by 2 inches. As many of you know, these are neutron and gamma ray sensitive. And the reason for this is the actual detection and interactions that the two particle types go through within our active volume. So an example for a given light pulse height, we can see that there's a difference in the tail region. When we take the ratio of the tail region to the total, we can discriminate particles with high confidence. So the top plot shows the still beam at 35 keV, while the bottom shows the EJ309. So you can see the two different clusters, or two clusters of data points that indicate neutrons and gamma rays. So before I go into the details and all that, I just wanted to show this, and I thought this was really neat. So the collaborations actually predates my experience as a PhD student, where it all began with design concepts and MCMPX polemi, followed by some validation measurements to kind of figure out which one was the best design. So that happened in 2012. And then in 2013, a prototypical design consisting of 16 EJ309s was taken to Ispra, Italy to measure some plutonium metals and some MOX canisters. And then the bottom two images are experiment campaigns that I was fortunate to be part of. So the bottom is our passive measurements from last year. So we were able to measure plutonium metal plates with the fast neutron multiplicity counter, and then just this past end of August, we were able to do active measurements with the same system. So when you combine these fast neutron detectors into a system that functions as a multiplicity counter, there's a lot of advantages that are gained from that. So one of the advantages are due to the detector response, as well as the system in general, we have much faster timing properties. So we're looking at timing resolutions on the order of around a nanosecond for full width half maximum. The second advantage here is we're directly detecting the fast neutrons that come from the fission event. So we don't need any moderating material to downscatter those neutrons. And what this allows us to have is a really short die-away time. So the plot with a blue curve shows the actual measured die-away times for this campaign. You can see that the die-away time is on the order of tens of nanoseconds. A third advantage which is basically what happens is because of the nature of these detectors, which are recoil detectors, we're actually able to retain a portion of the initial neutron energy, basically retain the neutron energy deposition. And this allows us for additional capabilities such as spectrum unfolding. So those are some plots of the unfolded spectra from last year's passive measurements. And finally, due to the time scale, so our system works on a nanosecond time scale, and due to that, we have very low rates of accidental correlated counts. And this consequently allows us to have lower uncertainty for fixed measurement time. So in the past, like I mentioned before, last year we were able to show with a passive measurement that we can actually produce this mass calibration curve as a function of the neutron doubles count rate. We've shown that we were able to estimate and assay these samples to a percent difference of plus minus 2% of the actual mass. Also with the estimated mass having a low uncertainty. So going from passive to active mode, we had to do some changes to the system design. So we were informed that we would have two interrogative sources available to us. So we had two Amelie neutron sources, which with an activity of around 50,000 neutrons per second. And so in order to place these in our system, new components and features were added. So one of the things we designed a machine were these polyethylene moderators or reflectors for the Amelie sources. So the Amelie sources were placed on the bottom of the system as well as on the top. The second new feature, I guess, or component would be compact electronics. So we actually upgraded our electronics so that it would fit all on a single crate, and so obviously our form factor for the system was decreased there. We also did some 3D printing of our still beam detectors. So we couple these detectors in-house, and so we wanted to 3D print some casings to allow for structural integrity. Plus they look cool, and they're maize and blue naturally. And the last thing we implemented was some new detector holder structures. So that allows us to have some more variability in the source or sample to detector distance. The last feature that we implemented were some special acquisition techniques. So one of the ones we implemented was an onboard photon rejection acquisition technique, which allowed us to mitigate our data throughput. So there were a few objectives, basically, that we have for this year's campaign. So the first objective was to measure neutron multiplicity counts from induced fissions in uranium samples. And we had samples of various mass content as well as various enrichment. Second objective, we wanted to try to produce the mass calibration curve and subsequently use that calibration curve to estimate the fissile mass. And the third objective here was to investigate our system's sensitivity to divergence scenarios. And I'll go into more detail later on. So the three sets of measurements that we had were certified reference materials 146, 149, and as well as some uranium oxide pins. For the sake of time, I'll just focus on two of these cases. But as far as the details go about these sources, so on the left here is shown the CRM 149. So all of these reference material had an enrichment of 93%. And they varied just based on the fill height of the actual sample. The 146 was kept at the same mass, but the enrichment was varied. As for the uranium pins, so we had an assembly of 32 pins, and each of them had 75 grams of uranium, and the enrichment was around 16%. And so the idea was here we measured different configurations by taking out one pin, and then 2 pin, 4 pins, and so on and so forth to see when our system can actually detect and identify that there was a diversion that occurred. All right, so for the first set of results, this is for the CRM 149. So the data and the plots here shown are for a 10-minute measurement and a 60 keV applied threshold, and that's approximately around a half MeV neutron energy. So the blue, red, and green curves show the singles count rate, doubles, and triples count rate, respectively, with the standard deviation error bar shown. So it's a good thing that you can't see the error bar. But for today's analysis, we wanted to focus on the actual doubles rate. So with the uranium oxide, there were other sources of single uncorrelated neutrons, such as alpha N reactions. So looking at the doubles rate is more indicative of the actual fissions inside the sample. So in order to kind of just prove our concept of calibration curves, we took our full data set here, and we took a subset of that data, and we deemed these as calibration samples. And what that allows us to do is we can fit the calibration curve to these calibration samples, and here I use the second order polynomial. So then what we would do is we take the remainder of the data that was not used for the calibration curve, and we deem these as assay samples. And then finally what we can do is we can estimate the mass of the samples with the previously produced calibration curve. So the table on the right there shows the actual mass, the estimated mass with the uncertainty included, and this is just counting statistics. But what we, our final results were that we were at estimating the mass within a plus minus 7% within a 10-minute measurement time. So for investigating the pin diversion sensitivity, some of the questions that we were trying to answer are, how many pins do we have to remove such that we notice that something is missing from the full assembly? And how does that sensitivity change as you increase your measurement time? So basically what the idea was, again, with those different configurations, we wanted to see when we have a greater than 95% confidence that something had been removed. So in order to show this, basically we wanted to look at the relative difference in the neutron doubles count rate to the base case, which is the full assembly 32 pins. So the plot here shows the relative difference for all the different configurations, and the x-axis shows how many pins were removed. And this is for a 1-minute measurement time, and so the gray area above shows the 2 sigma confidence interval of our full assembly. So the idea is we can see that for 1, 2, 4, and 8 pins removed, they all lie within that gray area, so we cannot detect those diversions. However, the cases where we remove 12 and 16 pins are well outside that gray area. So we conclude that for a 1-minute measurement time, we can detect a 12-pin diversion scenario, which approximates to around a 900-gram removal. So to see the behavior, or to see our sensitivity as a function of the measurement time, we can look at measurement time of 3 minutes. So we see that the gray area is decreasing because we have more statistical confidence. And so for this case, we can see that we are able to detect 8, 12, and 16 pins removed, while we are still unable to detect the 1, 2, and 4 removals case. So for 3 minutes, we can detect up to 8 pins. And then for a 5-minute measurement, we can see that we can detect up to 4 pins removed from the full assembly. And so to conclude, we basically successfully measured neutron multiplets from induced fissions. These fissions were induced with amyl neutrons. And so we were able to induce fissions in samples of various mass content as well as enrichment levels. And we also were able to measure different configurations of uranium pins. We were able to successfully produce a mass calibration curve with the small data set that we had. And we estimated the mass within plus and minus 7% of the actual mass for a 10-minute measurement time. And finally, we were able to investigate how sensitive our system is to seeing diverted pins. So we can say that we're sensitive to 4 diverted pins with a 95% confidence in 5 minutes. So with that, I would like to acknowledge our INL collaborators, so David Chichester, who, for his continuing support and work with us. And with that, I thank you for your time. I want to also especially thank Charlie Sosa and Scott Watson for helping out during the experiment. And for anyone who missed the demonstration, I'll be there after this session. So please come on by, and I'll take any questions.
If they lose more than 1 MeV, then they're below the lithium-7 alpha N threshold. And then once they exit the americium dioxide, then they move in and start interacting with these lithium compounds. And so, of course, we don't